All right then. Today's lesson is lesson number 3. So Unit 1 kinematics, lesson number 3, acceleration. Now acceleration is another vector quantity, so it does have a direction. So I also have this PowerPoint. You have this PowerPoint as well. It's on the Google site. Okay. And we're going to go over some things. So first, let's say we're taking a picture of a plane. And we took multiple pictures at the exact same time interval. So maybe exactly 1 second later for each picture, or 1 minute, whichever you like. Now, after each time interval, if the plane has moved the exact same distance, well, then we can conclude that, well, the plane's covering the same distance in the same amount of time, therefore its speed is remaining constant. So our velocity time graph would look something like this, just a straight horizontal line. However, if we saw something like this, where initially the plane was covering small distances, but then over different time intervals, successive time intervals, greater and greater and greater distances, we can conclude that, well, if the plane is covering greater distances over the same time interval, it's getting faster, right? And we're going to look at the case where it gets faster at a constant rate. So we're going to have a straight diagonal line like this. In this case, I just have the plane starting off with a velocity of 0. Okay, so our velocity time graph would look like a straight diagonal line. Right? And this is what acceleration is. Acceleration is the change in velocity over unit time. Our equation can be written like this, where we can expand that a little bit. Change in velocity. Remember, change in anything is a final minus initial. So we can write acceleration as final velocity minus initial velocity over the time interval that those two velocities changes have occurred. All right. Now in this case, this motor vehicle, it's getting closer and closer and closer and closer. So it's covering less distance for each successive time interval. So in this case, it's slowing down. So what would a position time graph look like? Well, a position time graph would be a curve. Right? If you have an acceleration, your position time graph is curved. Now in this case, right, let's just look at our position. Our position is initially 5 meters in a forward direction from some origin. It comes down with a fairly steep slope, a negative slope though, so it's moving quickly towards the origin. And then it passes the origin, and the slope is changing. And then they start coming back. So when does that slope equal 0? It actually equals 0 right here, right at the bottom. If you were to draw a tangent right at the bottom, that would be a horizontal line. And so your slope would be 0 there. Now remember, the slope of a tangent on a dt graph or a position time graph tells you the velocity. So this is very interesting. This tells us that the velocity at exactly this time is 0. We can do something similar, like a little experiment. Just look for something. Here, I were to take this and simply throw it up and have it come down. So it goes up, right? Changes direction and comes down. That's exactly what happened here. We changed directions. Initially moving away from the origin and then suddenly turning around and now starting to head back towards the origin. And at that same point where we changed directions, speed became 0. The same can be true, the same can be said if you throw something straight up. If you throw something straight up, once it's reached its peak of its motion, it changes direction. You can also say right there at the peak, its velocity is 0. Of course, its acceleration is not 0 because its acceleration, we'll talk about gravity on another day, but its velocity must be 0 at that point. In fact, if you were to draw this as a velocity time graph, it would look like this. Right? Initially moving away from the origin, hence the negative slope. from this case. And then coming to 0 right when we change directions. And then the slope becomes positive right here because we're running back towards the origin. So the slope becomes positive. Now, if we were to draw this as an acceleration time graph, the interesting thing is the slope of a velocity time graph is our acceleration, just by definition, because your slope is the rate at which something changes. And that something is whatever your y-axis is. Right? So here we have our y-axis, which is velocity, our x-axis is time, so our slope is the rate of change of velocity, and that is the definition for acceleration. So the slope on a VT graph tells you acceleration. And this is just a constant slope, so your acceleration time graph would just be a positive value, a horizontal line, unchanging. And those are the only situations that I'm going to give you. In grade 11 physics, we're never going to talk about a situation where acceleration is changing. It's always going to be constant if there is any. And so it'll always be a horizontal line, either at a positive or negative value, or at 0 if there is no acceleration. So now there's something I have to talk about, speeding up and slowing down. So let's go back to our handout. I put a very important point down here, which is a misconception. The word deceleration, we don't use that in physics. It's confusing and it lacks information. Now in English, when we use deceleration, we mean something slowing down. But in physics, you can have an acceleration, either positive or negative, and still be slowing down. Why? How is that possible? In physics, acceleration could mean speeding up, it could mean speeding down. But the main purpose of it is to indicate some sort of change in velocity, whether you are speeding up or slowing down. So how does it mean both? Well, it means both, or it could mean both, because it is a vector quantity. So you can have a positive value for your acceleration, or you could have a negative value for your acceleration. So let's look at an example. Let's say we have a person, okay, and the person is at rest, and then they start running to the right. And they run to the right at an increasing rate. So they're going faster and faster and faster. So our velocity is to the right. And because we're getting faster, we can say our acceleration is also to the right. Okay. Well, what happens sometime later if this person decides that they want to slow down and come to a stop? They're tired. Well, initially they are moving in this direction. They're still moving in this direction. They never move backwards. But if they're going to slow down, that means that velocity is getting smaller and smaller. It's actually changing. And it's changing because our acceleration is now directed in this direction. If you want, we can call our right direction positive, and so this acceleration would be a negative acceleration. Now, if they come to a stop and they're still accelerating, then they're going to start running backwards. Okay? And if they're running backwards, let me just continue the example. If they're running backwards and their acceleration is still in this direction, then they're going to move faster and faster and faster until they get tired again and want to come to a stop. If you're moving in this direction and you want to come to a stop, you need to accelerate in the opposite direction. So we have 4 cases here. The first case is when acceleration and velocity are both to the right and we are actually going to speed up. We're getting faster. Then our second case is when velocity is to the right but acceleration is to the left. This is when we get tired and we slow down. Our third case, third case was over here. Now we're moving backwards and our acceleration is still backwards and we're speeding up. And then we get tired again, so we accelerate in the other direction to slow down. Notice that speeding up occurs when velocity and acceleration are in the same direction. Right? So velocity and acceleration are in the same direction. However, when we're slowing down, notice that velocity and acceleration are in opposite directions. Opposite directions. So this is how we tell if something is speeding up or slowing down. We need information about their acceleration. And since it's a vector, that information includes direction, and the same with velocity. Simply saying something is decelerating does not tell me the direction of that acceleration. So we don't use the word deceleration because even though in English we use it to mean something is slowing down, in physics it's not a vector quantity. It doesn't give us the information we need to actually predict what the next motion is going to be in the system. So in this example, we have a bird starts flying south. Its motion is described in the velocity time graph to the right. So let's look at this. Our y-axis is velocity, because it's a velocity time graph. It's in meters per second. You should always have your units. And the positive direction is north. So anytime there's something above the x-axis, we know the velocity is north, and anytime there's something below the x-axis, we know the velocity is south. That would be the opposite of north, right? Remember, north is just negative south. And then, of course, our x-axis is time in seconds. So first question, determine whether acceleration is positive, negative, or zero for each section. So remember, acceleration is the slope on a VT graph. So in this case, the slope is negative. So we have a negative slope. Here it's a horizontal line, so our slope is 0. Here we have another negative slope, so negative acceleration. And here again, 0. And then all throughout E, that's a positive slope, so positive acceleration. And then a horizontal line, so constant velocity, no acceleration. Now in part B, it says if the bird is speeding up or slowing down in each section. So section A, we have a negative acceleration, and also the value of our velocity is between -2 and -4. So the value of our velocity is negative. So we have both a negative acceleration and a negative velocity. That means they're in the same direction. So right here at A, we're going to speed up. And you can see how it goes. Initially we have -2 meters per second and then -4 meters per second. So the magnitude of that became greater. Over here where there's 0 acceleration, well, nothing's going to happen. It's constant. So we're not going to speed up or slow down. Here, negative acceleration with a negative velocities. Again, speed up. Here, constant. Now here for E, well, what's happening? Here we have, let's split E into two parts here. So below the x-axis, we have a negative value for velocity, but yet the slope is positive. So they're opposite values. So we are slowing down here. Slow down. And you can see over time, I mean, here you have -6 meters per second, 4, 2, so that magnitude is getting smaller. But then we change directions. Now we're heading in the positive direction right here, where our velocity is positive and our acceleration is positive. So here we speed up. And you can see that as well. Over time, we're going from 0, 2, 4, 6, until we reach once again, a constant velocity. So no acceleration. That means acceleration equals 0. Part C. the value of the acceleration where it is not 0. So that would be at A, C, and E. So let's start with A. So what we're going to do is actually calculate the slope because it wants to know the value. So we're going to take final velocity minus initial velocity over that time interval. So acceleration equals final velocity minus initial velocity. That's our rise over our time interval. So that's rise over run, right? Our slope. So the rise, final is minus 4 minus initial, which is minus 2, all over our time interval of, well, between 0 and 1, so just 1 second. Now this is a double negative, so we get minus 4 plus 2, which is negative 2, divided by 1, which is negative 2. And then the units would be meters per second. So over here we have meters per second. And in our denominator we have seconds. So that's meters per second, or simply meters per second squared. What those units mean is, let me just write meters per second per second. What that means is how many meters per second something is changing every second. And so if your acceleration was 1 meter per second squared, well then you might start off at 0 going 0. 1 second later, you're going at 1 meters per second. Another second later, 2 meters per second. Another second, 3, 4, 5. So every second your speed is increasing at a rate of 1 meters per second. So those are the units for acceleration, meters per second squared. Okay? And that negative is telling us that it's negative north, which is the same as positive south. So we can say, if we want, that's positive 2 meters per second squared south. At C, at B it's 0, so we don't need to calculate that. But at C, let's do C. Again, acceleration is our rise over run. So final would be minus 6 minus initial, which would be minus 4. There's another double negative. And it occurs between 3 seconds and 4 seconds. So we have a 1 second interval of time there. Minus 6 plus 4, again, we're getting the same thing. And you can see that. It looks like it's the same slope. So we're doing all right. It should be 2 meters per second squared south. All right, next, let's do this big one, E. So for E, same thing. Final minus initial. Your final is over here at positive 6. Minus initial, which is down here at negative 6. Over our time interval, which looks to be between 7 and 10. So that's a 3 second time interval. And we get a double negative. So 6 plus 6 is 12 meters per second. In an interval of 3 seconds, which would give us 4 meters per second squared, and it's positive value, so that's telling us the direction is north. So for part D, it says when the bird changes direction. So you change your direction when you're going from one direction to the other direction. So in this case, right here is when we changed our velocity from negative to positive. So right there is where we change directions. And how can an object accelerate without speeding up or slowing down? Well, that can happen if, let's say you're in a car and you're just driving in a circle. It's not the greatest circle, but if you're driving in a circle and you're going at the same magnitude or same speed, so let's say you're driving in a circle at 20 kilometers per hour. Now, your magnitude's not changing. That doesn't mean you're not accelerating, because acceleration is a vector, and it means that the change in velocity over time, and velocity is also a vector. So even if your magnitude isn't changing, because your direction is always changing, so here you're this way, here you're that way, and so on and so on and so on, because your direction is always changing, you are still accelerating. That is acceleration.